Welcome to this lecture series in real analysis. In this lecture, we'll look at a logical concept. We will not need a lot of real analysis concepts. It's just a pure set theoretic and logical exercise that we will perform, but it will be of great importance to us. So let us recall roughly what we will need. So we need, of course, to know at least what are real numbers, but not too much of that. This lecture is mostly about sets. We need to know what are sequences. So a sequence in a set X is a list of this sort, an infinite list where each of these are elements of the set X. We also denote such a list like this or like that, or also if we are feeling lazy, which we frequently will, just like this, when there is no confusion. A more formal way to look at a sequence is as a function with the domain as the set of naturals. You can think of the first element of the list as the value that f takes on 1, the second element of the list as the value that f takes on 2, and so on. So one can easily think of this as a function, and one can think of a function as that. So the formal definition is this, but once we agree that this formal way of expression can be equivalently written this way, this becomes formal too. Okay, we need to know about subsequences. So if we are given a sequence, something like that, in a set X, then a subsequence is anything of this sort, where this is the case. So whenever you choose an infinite list of this sort, you get a subsequence of a given sequence. So we looked at it in detail. We also looked at the formal version of this, but let me not recall it here. If you like, you can go back to the lecture and look at it. Okay, so with that, let us move on. Here are some problems for practice. And now let us get started. So first, we will define this notion of ultimately. So fix a sequence in a set X and fix a subset of the set X. Okay, so just for the sake of a picture, we can draw one. So think of this as the set X, and somewhere inside we have the set A. Okay, and just give me 1 second. And you can think of a sequence, this thing xn, as a bunch of points labeled by natural numbers. So some of them may lie inside A, some of them may lie outside A, and so on. ... So it's a hodgepodge of a picture, but I'm sure you get the idea. So we have a sequence and we have a set A. Then we say that this statement, let me isolate it. We say that xn is in A ultimately, and put a bracket and write n inside it. So we say this to mean, that there is a natural number n such that whenever little n is at least capital N, we have xn in A. So note that this language is very, very aptly chosen because what is this saying? It is saying that beyond a certain point, if you think as natural numbers as time, think of 1 as 1 unit of time, 2 as 2 units of time, and so on, and a sequence as something that is evolving over time, then what the statement says is that after a certain timestamp, all the things all the things that appear after that lie in A. So eventually or ultimately, xn always lies in A. And that is exactly our definition of ultimately. This thing is important, technically, the thing in bracket, because we want to say ultimately over what? This is indicating to the time variable, if you will. So this n is indicating here, meaning after a certain large n, all the n's have the property that xn lies in A. So that's what this concept is all about. It's a very, very simple concept, but it's a very it just saves a lot of writing, and it is easier for humans to understand. Every time writing this may only get in the way, even though at times we have to resort to this. At times you have to unravel the definitions, but this is already fairly clear. Okay, so much for the definition of ultimately. Let me change the color so as to emphasize. Yeah. And let us look at an example. So we have this sequence, xn equals 1 by n. So again, to recall, if this is 0 and this is 1, then this is x1, this is x2, this is x3, x4, and so on. So these come closer and closer to 0. And here is something that we can immediately say. So or I don't know how to say this, note that, or then, or before that, let epsilon be greater than 0 and A be this set, or maybe I will put a closed interval here. So to picturize, let's say this is 0 and A is this set now. So this thing is A, this closed interval, that is A. And here is the statement that we make. Then xn lies in A ultimately. So what does this say? This says that after some very large n, or large enough n, all the xn's will lie in this interval, which is intuitively clear because x1 is here, x2 is here, and after some point, the xn's will enter this region and will never leave because they are coming closer and closer to 0. The formal justification you can make by the following statement. I mean, part of the justification you can make by using this, which we proved earlier. Just use this fact and the fact that this is a monotonically decreasing sequence. I don't know if I defined this notion of monotone decrement. If I didn't, I will do it later, but as of now, it just means that this keeps on decreasing. That's what monotonically decreasing means. Right? As n increases, this decreases. So just use this fact and the monotonicity to establish this. Okay. So here is a cousin notion of the previous one. Again, fix a sequence in a set X and let A be a subset of X. Then we say that xn lies in A frequently. Lies in A frequently over n if so if what happens? If for all natural numbers n, there is some natural number at least that much, such that xn in A So this seems to be a very complicated way of saying the following, or equivalently. What it is saying is the same as what I'm going to write. Equivalently, xn in A, or okay, if you collect the n's for which xn lies in A, then this is an infinite set. So in terms of the temporal understanding, if you think of the natural numbers as time instants, then this statement is saying that the sequence visits the set A infinitely many times. Okay, that's what frequently means. It may not completely align with our intuitive understanding of the word frequently, but this is how we choose to define it. So one could also have said that xn in A infinitely often. That would have been a better definition. This seems to convey a different message, but anyway, that the definition is what it is. All right. You can also equivalently say that there is a subsequence of xn such that this happens for all k. Okay, so this equivalence is an exercise. It's a very simple definition. It's a very simple definition, and all I'm asking is for you to verify these equivalences. Okay, so now let's look at some examples. So before we look at examples, here we have defined something for belongingness. One could have equally defined it for not belongingness. We could have said that xn does not belong to A frequently over n if if for all natural numbers n there is a natural number at least that much, such that xn does not belong to A. So such variants I will not be defining separately. We should be able to supply the requisite definitions for ourselves. So now, here is an example. We define this sequence xn as -1 to the n. So for odd naturals, we get -1, and for even naturals, we get 1. So one can easily see that xn is greater than equal to 1 frequently. Or let me write xn is greater than 0 frequently over n. Now you might say, well, we haven't said anything about greater than here or less than there, but again, one can supply the correct definition here. In terms of belongingness, we could have equally written that, we could have written it in another way, that xn belongs to the positive reals frequently. That confirms much more to this way of writing, but this is completely fine. Okay, so that's a very simple example. Another very simple example is define xn as equal to n for all natural numbers n. Then xn is odd frequently over n. Why? Because it is odd infinitely many times. And xn is also even frequently. Right? So both concepts of ultimately and frequently are very, very easy. And with that, let us establish a final equivalence, which is just an exercise in basic logic. So you have some sequence in a set X, and we are given a subset of X. Then one and only one of the following holds. So the first one is that xn lies in A ultimately. Either this holds, or sorry, I have messed up. So I don't mean to write the last one. Yeah, now it's what I want to write. So again, we have a sequence in a set X, and A is a subset of X. Then one and only one of the following holds. either xn lies in A ultimately, or x1 is away from A. Sorry, xn is away from A frequently. Both, of course, over n. So it's an exercise, but let me maybe give details. But how do we start? So assume 1 does not hold. Assume 1 does not hold. We want to show 2 holds. Want to show that 2 holds. So this will finish the proof. Okay. Now since this does not hold, meaning whenever you pick a natural number n, there is some natural number little n exceeding it, which violates this property. Because if there were a natural number n for which no little n exceeding it violates this, then this would become true. But we are assuming this is false. So for each natural number n, you can find some little n greater than equal to it, such that xn does not lie in A. And that's exactly what this means. That's the definition of frequently not lying in A. So I said I will give details, but I have given details, but I'm not writing them. I feel a bit lazy. Okay, so you can write the details for yourself. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.